folks were assigned a problem they could complete to get points back on the test, and if you're going to do that, that's due today. So if you you could either bring it, I've already got some of them, but if you could bring it by my office or upload it. Actually, I don't know if it'll let you upload to Canvas. So you could email it to me, I guess, if you're going to submit it electronically. And then we have a quiz Thursday. That'll focus on the exponents and radicals, so like rational exponents and radicals. Up through what we covered today. I think, there's a decent chance we might get through the equations with radicals section, and if we do, that'll be included on the test. It is already included on the practice quiz. And then of course we have recitation today for folks who can make it in 212 at 11. Does anybody have any questions before we dive in? Questions on practice exercises? Or questions about the quiz? Okay. All right, so we're going to just keep working with radicals, adding and subtracting radicals. We did this a little bit last semester. We're just going to do it some more. We're going to see it with radicals with different indices. And then we'll do some multiplication division of radicals. That's pretty fun. And then solve some equations. So the idea is that you start by simplifying your radicals. If you happen to have the same radicand, the number inside, you can combine like terms. So root 2 is already simplified, but 8 we could factor. It's 2 times 2 times 2, and there's our pair of 2's. We got a pair of 2's, we could bring 1 out. So we have root 2 plus 2 root 2, and now we can combine like terms. Altogether we have 3 root 2. Let's do another one. We're going to start by simplifying. So simplifying means really we're going to start by factoring. 24 is 3 times 8, or 3 times 2 cubed. 81 is 9 times 9, so that's 3 to the 4th. And I'm going to write that as 3 cubed times 3. And I'm choosing to write it that way because we have cube roots, right? So I'm looking for perfect cubes that I can take out. So we have 2 times the cube root of 3 plus 3 times the cube root of 3. And altogether, 5 times the cube root of 3. On these numerical ones, you can always check your answer. Like, you can enter this in your calculator, see, get some decimal approximation, and then enter that, and you'll see that they're identical. Questions? All right, let's do another one. How do we start this one?
Back to the square root of 24.
Yeah, right. 24 is 3 times 2 cubed, right? We did that in the last one. I'm going to call that 3 times 2 times 2 squared. I'm writing it that way because this time it's a square root. What do we do with the next radical? Yeah, we could split up a radical over division. We're going to do that. The reason we want to do that is because we can rationalize that denominator. What do we need to do to accomplish that? root 2 over root 2. Right, the root 2 in the bottom is the problem, and we could kind of fix it just by multiplying by rad 2 on the top and the bottom. So now, let's see, that first radical, we'll take out the 2 squared. So we have 2 root 6. And this is root 6 over 2. And I guess there's a couple different ways you could think about this. I'm going to just deal first with the fraction. So like this 2 root 6 is 2 root 6 over 1, and I'm just going to get a common denominator. So now we have a common denominator of 2. We have 4 root 6 plus root 6, or 5 root 6 over 2. I often leave it written like this. Some people like to write it as thinking of a single coefficient. Like in that expression, 5 root 6 over 2, the coefficient of root 6 isn't really 5. It kind of looks like it is. So for that reason, a lot of people choose to write it as 5 halves root 6. Either is fine, as far as I'm concerned. Okay, let's do some more. We got fractions inside radicals, so we'll start like we did the last one. We'll split those up. So we got root 2 over root 3a minus. Now we have that factor of 2 outside. That's like a factor of 2 over 1, and I'm just pointing that out because now I can write this as a single fraction as 2 root 3 on top over root 2a. All the radicals that appear in this expression are already simplified, right? Like root 2 and root 3 and root 2a and root 3a are already simplified. So there's 2 things that we need to accomplish in this problem. We have to rationalize denominators, and we need to get a common denominator and add it. It doesn't really matter which one you choose to tackle first. I usually rationalize denominators first, but you could get the common denominator first if you prefer. I'm going to go ahead and just zap the first fraction with a root 2a on the top and the bottom. And root 3a on the top and the bottom over here. What is the common denominator? What do we get? Or getting started, like, what do we end up with in the denominator? Like inside a square root, right?
Yeah.
Oh, I get 6a squared. You know what? I said I was going to rationalize denominators first, and I actually got a common denominator first. Whew. Feels like a Monday or something. Well, let's go ahead and do it this way. Right? It works out fine either way. We have root 6a squared, which is, of course, a times root 6. Up top, we've got root... Oh, let's see. This first product, what does that simplify to?
2 square root of a.
2 square root of a, yeah, because we have 2 factors of 2 in there. So 2 root a minus, and now what about this guy over here?
6 root of a.
6 root of a, yeah. So we have 2 root a minus 6 root a on top. That's negative 4 root a. Now let's rationalize the denominator. Liz, question. Did I make a mistake? Okay.
I'll figure it out.
Okay. So if we rationalize now, we can multiply by root 6 on the top and the bottom. So up top, we have negative 4 root 6a. What do we have on the bottom?
Six,
6a, and then there's one last step. What is it? Yeah, we got to reduce. You know, when you get results that are fractions, we always want to make sure we write them in a reduced form. So let's see, we could take out 2. So negative 2 root 6a over 3a. Questions? Okay. All right, let's multiply and divide some radicals. So here we're just mostly going to be using the rule that says we can, we could split up radicals over multiplication. We can also combine them over multiplication. And that's the basic rule that we're going to use. You just have to be careful and make sure that we can only do this if the radicals are the same index or the same order. So multiplying these radicals, root 5 times root 2, we're just going to do the multiplication inside and get root 10. We've already used that. I mean, we used that already when we rationalized denominators. This is nothing new. I'll do one more here. We have the cube root of 6 times the cube root of 4. And we end up with the cube root of 6 times 4. Now, we could just call that the cube root of 24, but there's more to do. Like, cube root of 6 and cube root of 4 are themselves individually already simplified. There's no, we don't have 3 of the same factor in either one of those. But now, once I combine them, let's factor these. We have 3 times 2 and then 2 times 2. So combining them, multiplying inside, did give us a group of 3 of the same factor, so we could pull out that 2 times the cube root of 3. Anytime you're doing it, operations on radicals, every step of the way, you just want to kind of reevaluate where you are and say, can I simplify this? We started with radicals that were already simplified. We couldn't do anything to simplify these. Once we combined them, we saw that we did have, in fact, a factor to take out. All right, we multiply a couple fifth roots, so we're going to look for groups of 5 of the same factor, or perfect fifth powers inside. There are no perfect fifth powers in each of these radicals individually. However, let's see, I've got 2 cubed times 2 cubed. What I'm doing right now is I'm combining them, and I'm just choosing to kind of put the numbers first, and I'm going to group the a's together and then the b's together. So we have a cubed times a squared, and then b to the 4th times b cubed. And I'm going to rewrite these factors for my own convenience, right? 2 cubed times 2 cubed is 2 to the 6, but I'm going to write that, that's the fifth root. I'm going to write that, instead of 2 to the 6, I'm going to write that as 2 to the 5th times 2. A cubed times a squared is a to the 5th. I'm going to write it like that. B to the 4th times b cubed is b to the 7th. How am I going to write that? And I'm doing this just to make it more convenient for me to be able to simplify. There are people who will say, I'm just going to write it as b to the 7th and understand that I'm going to take out the factor of b and be left with a b squared inside. That's fine to do. But sometimes as I'm kind of, quickly working through problems, you've all witnessed this, I can make mistakes. So I try to set myself up in such a way to minimize the chance that I make a mistake. So we have 2ab, and then the fifth root of 2b squared. So these examples, we just had individual radicals that we were multiplying. They were the same index. We combine those under a single radical and then simplify. We're going to do some more multiplications of just expressions that involve radicals. So I might have an expression where maybe I've got some addition and subtraction and multiplication going on. This is definitely a multiplication problem that involves radicals. That inside the parentheses, I'm subtracting some radicals. Note that those radicals are already simplified. I don't have a common radicand, so I can't do the subtraction. The only thing for me to do right now is to distribute that factor of the square root of 2. So we get root 2 times 3 root 5 minus root 2 times 4 root 2. And now individually, each of those products, I just have single radicals, right? So square root times the square root, we could do that multiplication inside. So that first product is 3 root 10. And what do we get for the second product?
8.
Say that again?
8.
8? Yeah, root 2 times root 2 is 2, so we end up with 4 times 2, or 8. At the end, we always just make sure that give a quick look and make sure that all radicals that are in our result are simplified. 3 plus root 5 squared. How do we do that? What's our first step? Like, how do we want to think about that expression? It's a FOIL problem. Yeah. When you square something, we're multiplying it by itself. Over and over and over again. This is a recurring theme in last semester and this semester, and probably in it'll show up again if you take calculus or other math courses. We cannot distribute an exponent over addition. So if there's one thing, hopefully there's more than one thing. If there's one thing like I want us to take away from today and maybe even this semester, we can distribute an exponent over addition. So let's FOIL this out. I'm going to, my favorite method is to just set up that little table. So I've got 3 root 5, 3 and root 5. In the top row, we got 9, 3 root 5. In the bottom row, we got 3 root 5 and 5. We have our like terms along this diagonal. So we end up with, and we also have like terms along that diagonal. So 9 plus 5 is 14, plus 6 root 5. Questions on these examples so far? So far, all of our examples have dealt with, we are already working with radicals of the same index. And when we have radicals of the same index, that's when we get to just combine them in a single radical, do the multiplication inside. If we have radicals that we want to multiply that are of a different index, I usually start by converting to, we need to get them written as the same index, right, if we're going to multiply. And I usually accomplish that by writing the fraction exponent version first. I just find that it helps me out with that process. So this is 2 to the 1/3 times 5 to the 1/2. And what I want is a common, what I want is a common index of these radicals, what that means is I want a common denominator of these exponents, of these fractions. So that common denominator is 6. I'm going to write 2 to the 1/3 as 2 to the 2 over 6. Five to the 1/2 is 5 to the 3 over 6. And now we have a couple different ways we could proceed. One way is to just right now go back to the radical form. So this is the 6th root of 2 squared times the 6th root of 5 cubed. And now that we have radicals at the same index, we can combine them. I've got the 6th root of 2 squared times 5 cubed, which is 500?
125 times 4 is 500.
Yeah.
500?
So I said there was a couple ways we could proceed. From here, you could, if you wish, instead of going right to radicals first, you could write this as 2 squared 5 cubed all to the 1/6 power. And then that gets you right there.
You want to factor that to make sure there wasn't a sixth root there? Or
That's
just
a
no?
really good idea, but we already did it.
Oh.
Yeah. So, yeah, when you're combining them, you know, we usually start out with things factored because we're multiplying, but like here they were already, and it was a prime factorization, right? 2 and 5 are already primes. If these weren't already prime powers, instead of multiplying them first, I'd factor further, right? To be on the lookout for 6 powers. Other questions? Okay. All right, dividing. We already know that we need to rationalize denominators, and you know, we've been rationalizing denominators for fractions that look like this one, right? Where we just say, oh, I'll multiply by this radical on the top and the bottom. I think this might be over the last 2 semesters, like the 4th time we've probably rationalized this fraction right here. But we get root 3 over 3, right? Now, we here's a radical expression that involves division, and we have radicals in the denominator here. If I just multiply by root 3 and distribute, it'll take care of this one, right? But then I'll have a root 6 here, and that won't, I'll still have radicals. If I just multiply by root 2, it'll take care of this one, but not that one. And now you might be thinking, well, what if I just multiply by root 6? You know, would that take care of them both? As it turns out, no, it won't. So what does work is multiplying the top and the bottom by the conjugate of this expression. So if you're adding or subtracting 2 terms, the conjugate of that expression is what you get when you just change this. So from a minus to a plus, or from a plus to a minus. So I'm going to multiply the top and the bottom by root 3 plus root 2. Now on the top, that's pretty simple to see what we get, because I'm just multiplying it by 1. On the bottom, we have to FOIL. So across the top, our products are root 3 times root 3 is 3. Then we have a minus root 6. In the second row, we have a positive root 6. And root 2 times a negative root 2 is a negative 2. We have our like terms along the diagonals. This pair of like terms cancels each other out. And then this just gives us negative 1.
Would it be negative 1 or 1?
Oh, sorry. Yeah, 1. And of course, now we'll just write that as root 3 plus root 2. The conjugate always works, like multiplying by the conjugate always works, because it's sort of like saying, like we kind of know, we're guaranteed that like those radical expressions are going to cancel each other out. It's like thinking of this as how a difference of squares factors. If I want to view 3 as a perfect square, it's the perfect square of root 3. And I want to view 2 as a perfect square, it's the perfect square of root 2. Then this is how that difference of squares factors. And so that's 3 minus 2 or 1. Let's do another. I always start by just making sure that the individual radicals themselves are simplified. You know, like reduce the order, or make sure I take out perfect powers. These are already simplified. What's my first step here? How do I rationalize? Yeah, the conjugate. So this time we're starting with a root 6 plus root 2, so that conjugate is root 6 minus root 2 on the top and the bottom. Now we could set up the grid to find that product on the bottom, and I'll do that, but you might already know what we're going to get, because that is how the difference of squares factors if my perfect squares are 6 and 2. So we should get 6 minus 2, or 4. Let's just verify. Root 6 times root 6 is 6. This gives us root 12. On the bottom, now I've got, whoops, I'm actually just squaring. Hold on. One of these should be, I'll say that one's negative root 2. Negative root 12 and minus 2. So here are our like terms here that sum to 0, so those radicals cancel. Our like terms here give us 4. And for the product on top, let's see, 3 root 6 minus root 2 multiplied by root 6 minus root 2. So we have 3 times 6, or 18, and then negative root 12. On the bottom, minus 3 root 12, and then plus 2. We have like terms along the diagonals. Here we have a negative 4 root 12, and this gives us 20. So we have 20 minus 4 root 12. There's a couple things that we're going to need to work on. The first thing that catches my eye is that root 12 is not simplified. Right? That's a square root. 12 certainly contains a perfect square factor. It's 2 squared times 3. So root 12 is 2 root 3, and I can rewrite that now as 20 minus 8 root 3 over 4. What else can we do? Yeah, let's take out a 4 from the top, because we can reduce this. And then we have 5 minus 2 root 3 in parentheses over 4, and then we'll just cancel. So we get 5 minus 2 root 3. These two division problems happen to work out so that our result, it wasn't a fraction itself. A lot of the times you will still have a fraction, and that's fine, but the goal is that you don't have any radicals in the denominator if you do end up with a fraction, and then you reduce whenever possible. Again, the numerical problems you can always check on a calculator. You can plug this in, get an approximation, some decimal, and then see that you get the identical one, and you plug that into the calculator. Questions? Okay. All right. Well, one more section to go. Equations with radicals. The first thing I'll say is that it is possible to get extraneous roots when you solve equations with radicals. So you have to check. You have to check all your answers. The other instance, where we saw that we could get extraneous roots was when we were solving equations that had fractions. And finding an extraneous root amounted to just making sure that we weren't dividing by 0. Here we don't have that. You really do have to plug everything in and check out both sides and see that you get equality when you plug them in. So our basic procedure is, if you have a radical, you're going to isolate that radical, get it by itself, and then square both sides, or raise it to whatever power. If it's a cube root equation, you're going to cube both sides. You may need to repeat that process. If your expression has more than one radical, after one iteration of that process, you'll still have a radical left over, and then isolate and repeat the square both sides to get rid of the radical. And then just solve the resulting equation, which will either be linear or maybe quadratic, but it'll be an equation, a type of equation that we know how to solve already. But the new kind of procedure, the new thing that we're learning is how do we take this equation with radicals, get rid of the radicals to turn it into an equation we already know how to solve. So this radical, I would say, is already isolated because we're not adding any other term. You could divide both sides by 2 first. Sometimes I do, sometimes I don't. You'll get the same result either way. The isolating the radical is only a must if you're adding another term, right? So here I just have a coefficient on the radical. That's fine. Let's go ahead and square both sides. And when we square the left side, we have a product, so we're going to square both of those factors. So we have 4 times 3x minus 1 equals, what, 9x squared. This is a type of equation we know how to solve. It's a quadratic. Let's distribute that 4. 12x minus 4 equals 9x squared. And then we can gather all of our terms on one side, set it equal to 0, see if it might factor. So we get 0 equals 9x squared minus 12x plus 4. Let's see if this does factor. We don't have any prime terms or prime coefficients, so we have options, which means it'll take a little longer. Anybody got it?
3x minus 2.
Uh-huh.
3x minus 2.
Oh, okay. So it's a square. Two of the same factor, yeah. So that's 9x squared minus 6x minus 6x and then plus 4. Good. So now that we factored it, it's set equal to 0, so we're just going to set this, really the only distinct factor that it has, equal to 0, and we get x equals 2/3. Now before I state confidently that the answer, the solution of this equation is x equals 2/3, I'm going to check it. So let's see what we get. 2 times. So this is a big question mark here. Hopefully, if that checks out, we can put this to bed. Let's see, 3 cancels with the 3. So that radical inside, we just have 1. And those 3's cancel. And I think right now we can state with confidence that 2 times the square root of 1 is in fact 2.
What happens to the negative attached to the 1 in the radical?
Right here? Oh, so actually maybe let me include an intermediate step. So those 3's cancel? That's 2 minus 1. Other questions? Let's do another. Here's an equation with a cube root. That cube root is already isolated. What do we want to do first here?
Cube both sides.
Mm-hmm. Oops. So then when we cube both sides, on the left we get x minus 8 equals 8 on the right side. And that's pretty simple to solve. We get x equals 16. So we got just a linear equation that resulted from this. And then we're going to do a quick check to make sure that this does in fact work. Cube root of 16 minus 8. This is equal to the cube root of 8. And that is in fact equal to 2. Okay. Let's do another. Square root of x minus 1 plus 3 equals x. So here's an example where we need to isolate. The radical is not already isolated. I know because I'm actually adding another term. So I'm going to subtract 3 from both sides. And then we get square root of x minus 1 equals x minus 3. The reason that we have to isolate that radical first is like, if I started at the out the gate and I said I'm going to just square both sides, the result would still have a radical. If I square both sides, I have to FOIL this out. You'll still have that radical, and it'll be almost maybe a slightly more complicated equation. Once we get that radical by itself, then squaring will actually just get rid of the radical. So we have x minus 1 on the left side. What do we get on the right side?
X squared plus 9.
So we don't,
Can't over subtract.
we cannot distribute an exponent over addition or subtraction. So what do we get?
X minus 3, x minus 3.
Yeah. So we're going to FOIL that out. X squared minus 6x plus 9. We have a quadratic. I'll set it equal to 0, so I'll subtract x and add 1. Oops. I think this factors. At least I know if it does, it's just x and x first. That makes it nice and easy, or easier. What works?
Plus 5
Plus 5 plus 2?
minus 5.
Yeah, I think minus 5 minus 2, because we're going to get a negative 7 in the middle. So x equals 5 and x equals 2. It looks like we've got a couple solutions. We have to check them both. So let's check x equals 5 first. So the square root of 5 minus 1 plus 3. Is this equal to 5? Square root of 5 minus 1 is root 4. That's 2 plus 3 is in fact equal to 5. So that checks out. And for x equals 2, we have the square root of 2 minus 1 plus 3. Is this equal to 2? We get a 1 plus 3. No. 1 plus 3 is in fact not equal to 2. So this is not a solution. This is an extraneous root. That extraneous root is absolutely a solution to this equation that we got after we squared both sides. It just doesn't check out in the original.
test, would you want us to label it?
Like as extraneous? No, you don't have to label it, like you don't have to use the word extraneous, but you should indicate like that's not a solution and only this one is. Let's do another one. So here's an equation that's got a couple radicals that we're adding together. I need to isolate a radical first. Pick one to isolate. Like it really doesn't matter which one we attack first.
X plus 1.
What's that?
X plus 1.
So isolate that first radical. So subtract the square root of x minus 4 first. So we have the square root of x plus 1 equals 5 minus the square root of x minus 4. Now that we have isolated a radical, we're going to square both sides. The left side is pretty clearly going to just result in x plus 1. What do we do on the right side? Foil, yeah. So 5 minus radical x minus 4, 5 minus radical x minus 4. And I'm going to set up my little grid here. So along that top row, we got 25 and then negative 5 radical x minus 4. In the bottom row, minus 5 radical x minus 4, and then a positive x minus 4. We have like terms along this diagonal. And I guess we have some like terms along the other one, right? The 25 and the minus 4. We get, let's see, 25, x minus 4 plus 25 is x plus 21. And then minus 10 times the square root of x minus 4. We still have an equation with radicals, with a radical, but notice we started out, our first equation had 2 radicals in it. This one has just 1 radical. I know I'm making progress. What do we do next?
Isolate the radical.
Isolate that radical. So let's throw those other terms, those terms on the other side. I'll subtract x and subtract 21 from both sides. So we have minus 20 on the left. On the right side, we have minus 10 radical x minus 4. So the first example we did, I said, that radical really is isolated. We could square both sides right now. I'm going to go ahead and do the division just because I'll just be able to cancel. It'll be like, I'll end up with smaller numbers, which I find convenient. So it's really, I guess, a matter of personal preference as to whether you choose to divide by negative 10 first, but I'm going to do it. So we get 2 equals the square root of x minus 4. Liz, you look unhappy. Are you okay?
I'll be alright.
Okay. Do you need to talk about anything? Okay. What comes next? Square both sides. So 4 equals x minus 4, and we get 8 equals x. What's left to do?
Check.
Check. Always got to check these solutions. So check them in the original equation. If I check x equals 8, the left side is the square root of 8 plus 1 plus the square root of 8 minus 4. And we're going to see, does that give us 5? So now we have root 9 plus root 4, that's 3 plus 2. That does, in fact, give us 5. So
Do we have to isolate the other radical, or we just get the same things?
I don't know what that means. I mean, we
At
isolated.
the top, we just chose one,
Yeah.
and so it wouldn't matter which one we chose.
Nope.
We did the same.
Yep. It does. It makes no. If you have an equation with more than one radical, just pick a radical that you're going to isolate first and go with it. Other questions? Okay. So that's all I wanted to cover for new material. What I'm going to do right now is just hand out the practice quiz. You may choose to use this time to work on it. If you get through it, then there's no need to go to recitation.